The distinct yellow luster of gold is not a simple chemical property, but a direct manifestation of Einstein's theory of special relativity within the atom. While silver reflects nearly all visible light to appear white, gold absorbs blue and violet wavelengths, leaving behind the warm yellow hue we recognize. Gold possesses an atomic number of 79. This massive positive charge in the nucleus exerts an immense electrostatic pull on all orbiting electrons. To avoid spiraling into such a powerful nucleus, the innermost 1s electrons must travel at a significant fraction of the speed of light. Specifically, these 1s electrons in a gold atom move at approximately 58% of the speed of light, roughly 170,000 kilometers per second. According to special relativity, as an object approaches the speed of light, its relativistic mass increases compared to its rest mass. For gold, this relativistic effect increases the mass of the inner electrons by about 20%, fundamentally altering their behavior and orbital geometry. The Bohr radius of an electron orbital is inversely proportional to the electron mass. As mass increases, the orbital must contract toward the nucleus. The 1s orbital of gold undergoes a massive relativistic contraction, pulling it much closer to the nucleus than non-relativistic physics would predict. This contraction is not isolated. It cascades outward, causing the 2s, 3s, 4s, 5s, and 6s orbitals to also shrink significantly. The contraction of the 6s orbital brings the electron closer to the positive nucleus, which lowers its potential energy and stabilizes the orbital. While s orbitals contract, they also provide better shielding of the nuclear charge. This has a surprising opposite effect on the d and f orbitals. Because the contracted inner shells shield the nucleus so well, the 5d electrons feel a weaker pull, and their orbitals actually expand outward. The stabilization of the 6s orbital and the destabilization of the 5d orbital bring these two energy levels much closer together in gold. In silver, the energy gap between the 4d and 5s orbitals is large, requiring high-energy ultraviolet light to excite an electron. In gold, this gap is reduced to approximately 2.4 electron volts. This specific energy level corresponds to the visible blue light spectrum. When white light strikes a gold surface, the blue and violet photons are absorbed to promote electrons from the 5d to the 6s orbital. By removing blue from the reflected spectrum, our eyes perceive the remaining light as the rich metallic yellow we associate with pure gold. This same relativistic chemistry explains why Mercury is liquid at room temperature. Its 60s shell is so stable it refuses to bond with neighbors. In Mercury, the relativistic contraction of the 6s orbital is even stronger than in gold, creating a closed, chemically inert electronic configuration.
The high voltage of a lead-acid battery also relies on relativity. It accounts for nearly 80% of the potential in each cell. Relativity stabilizes the 6s electrons in lead so effectively that they do not participate in typical bonding, leading to the unique lead-4 oxide reactions. To model these heavy elements accurately, chemists must use the Dirac equation, which blends quantum mechanics with the requirements of special relativity. Relativistic effects become so dominant in the 7th row of the periodic table that elements like copernicium behave like noble gases rather than metals. Platinum owes its famous chemical inertness and catalytic properties to these same relativistic shifts in its 5d and 6s electron energy levels. High nuclear charge leads to high electron velocity, which increases mass, shrinks s orbitals, and shifts the color of the metal. Gold is one of the few places where we can see the consequences of special relativity with the naked eye in everyday objects. Relativistic quantum chemistry represents the boundary where our understanding of the very fast meets our understanding of the very small. Modern materials science would be impossible without these relativistic corrections, as standard quantum mechanics fails to predict the properties of heavy metals. While the lanthanide contraction also shrinks atoms, relativistic effects provide the additional shift needed to perfectly match experimental data for gold. The filled 4F shell in gold provides poor shielding itself, but when combined with relativistic S contraction, the overall electronic structure is uniquely altered. Relativity also introduces spin-orbit coupling, which splits energy levels further and influences how gold interacts with magnetic fields and light. These energy shifts allow gold nanoparticles to act as highly efficient catalysts for reactions that were previously thought to be impossible. The color of an element is a fingerprint of its energy levels. Gold's fingerprint is uniquely shifted by the speed of its own electrons. Relativity even affects cesium, giving it a slight golden tint compared to the silvery appearance of other alkali metals like sodium or potassium. Without relativistic stabilization of the lead 6s orbital, a car battery would only provide a fraction of its current voltage, making electric starters impractical. In Mercury, the relativistic contraction is so extreme that the van der Waals forces between atoms are the only thing holding the liquid together. The melting point of Mercury is nearly 400 degrees Celsius lower than its neighbor gold, a gap primarily caused by relativistic orbital stabilization. Relativity continues to influence thallium and lead, where the 6p orbitals also begin to show contraction and stabilization effects. Even bismuth, the heaviest stable element, owes its chemical properties and low toxicity to the relativistic shielding of its inner shells.
Electronic transitions determine what we see. In gold, the transition from 5D to 6S is the key to its color. Visible light ranges from 1.7 to 3.1 electron volts. Gold's 2.4 electron volt gap sits perfectly in the middle. Imagine a slider moving the absorption peak. Without relativity, that slider would be in the ultraviolet. Relativity pushes it into the visible blue. If we could turn off relativity, gold would be a silver-white metal, indistinguishable from silver or platinum to the naked eye. The noble metals are noble precisely because relativity makes their outer electrons so difficult to remove or share in chemical reactions. Computational chemists use the Dirac-Fock method to solve the many-body problem for heavy atoms while accounting for relativistic mass and spin. At the nanoscale, these relativistic effects are tuned by size, allowing for the creation of gold particles that can be red, green, or blue. High-precision spectroscopy confirms these relativistic shifts to within a fraction of a percent, proving Einstein's theories in a test tube. This field proves that chemistry is not separate from physics. The behavior of a ring on your finger is governed by the laws of the universe. As we synthesize heavier elements in particle accelerators, relativistic quantum chemistry will be our only guide to understanding their strange new properties.
The periodic table may lose its periodicity for superheavy elements as relativistic effects eventually overwhelm the standard patterns of the lighter groups. Advanced X-ray diffraction can now map the actual electron density in gold crystals, visually confirming the contraction of the s orbitals. The color of gold remains the ultimate visual proof that we live in a relativistic universe where space, time, and mass are deeply intertwined. From the yellow of gold to the liquid state of Mercury, Einstein's legacy is written into the very fabric of the elements themselves.